we've had a bunch of presentations over the last couple of days that have talked about some really great observing. I don't know about all of y'all, but for me, part of observing is making sure I know what I'm looking at. And we don't have the good fortune that the optical astronomy guys have of being able to put a finder scope on the device and tell whether something is there or not, because most of the time what we're looking at doesn't have an optical equivalent, at least not one that we can see readily. So there's all kinds of ways of solving that problem from the standpoint of positioning. I know that over the years there's been various things with resolvers and even potentiometers and encoders and all kinds of things to get people a semblance of exactly where something is pointing. In our particular case, with small antennas like I have, which is only a 3-meter dish, you can be kind of sloppy with it. But when you got something like the deep space outfits where you have a very narrow beam width, then pointing becomes a much bigger issue. Most of the mounts that you'll find are not really set up with any kind of fine granularity from the standpoint of a position system. Let me go ahead and see, hope this works. There we go. So anyway, as the top bullet says, any successful observation has to know where you're pointing, and that's something that this whole thing is about. And due to most considerations from a design standpoint, at least for radio astronomy antennas, most of them are altitude azimuth kind of mounts. Equatorial mounts are absolutely wonderful, but you don't, for the most part, there's certainly exceptions. You don't see a lot of radio astronomy antennas with equatorial mounts. As the bottom bullet says, the design of a positioning system can be local and very simple all the way up to remote and very complex. Several years ago, I published in the journal 3 articles that had to do with the development of my 3-meter dish, and it had a home-built remote, fairly complex positioning system and motor drive system that allows me to do tracking and all that kind of good stuff. But it was a laborious effort. I did the programming and I did the electrical design and all that stuff rather than buying systems that were out there. Not everybody's going to do that. I don't know if anybody ever copied anything design-wise that I put in the journal. I never got the inquiries, let's put it that way. But the systems can get fairly complex. The journal articles, if anybody's interested, were October of 21 and March, April of 22. Then there was a follow-on article past that talked about the software, where I wrote the tracking program and the raster scanning and all that kind of good stuff. That was all done in Python. This is a picture of, cut off some of it. This is a picture of my particular antenna. That's the overall unit. It's a 3-meter, which is pushing the limits of what my neighbors will stand. But it's fully automated and has a fiber optic, a gigabit fiber optic link that comes in through this PVC pipe into my house and up into my lab, as my wife calls it. And it's got several components that are for tracking and positioning, and they're both local and remote. If you see down here, I've got one of the boxes on the post here. It's got a local display of position, and then there's this is you guys will recognize that as being a Raspberry Pi computer, but that little computer is then the communication for the remote part, which sends the position back up into the lab for the tracking program and for other things. You look at the sensors. This is the Azimuth part of the mount, and this is a 1,000 point per revolution encoder, and this is a 8-to-1 spur gear setup. So in effect, I'm getting 8,000 pulses for 360 degrees. If you do that math, then you come up with 0.15 degrees per count. All of this is based on both the complex and the simple thing that I'm going to talk about here in a second, is based on quadrature encoders, incremental encoders. And these are very inexpensive import type encoders that are usually, some of them are magnetic, but most of them are optical. But they put out a quadrature signal, and the quadrature signal is important because that's the way that you can count up and count down without having to worry about any of the intricacies of doing that, so that you have two pulse streams, one stream leads or lags the other, and that's what allows the counter to go up or down. Now, normally, those are handled by a little microcontroller or a CPU in a computer to then feed into a counting routine. We'll show you how that can be different here in just a minute. But this is, that's the Azimuth encoder. And then here, if you look at, it's a little hard to tell, but this up into the middle of this part up here, there is a inclinometer that is on the elevation axis or the altitude axis. And those feed into the electronics here to both demonstrate or give the position both locally and send it remotely. Okay, so the design that I'm going to talk about today is at kind of the other end of the complexity spectrum from that. It doesn't have any computer, doesn't have any microcontroller unit. It involves an encoder, a cheap, inexpensive, I should say. In this case, 1,000 point per revolution quadrature encoder with a 6mm shaft, roughly 1/4 of an inch. A counter that I found off eBay that basically is a quadrature input 5-digit counter. And the unique thing about it, I mean, having it be a quadrature input counter is pretty unique. But the more unique part of it is that you can manually, through a couple of switches, you can configure the scaling factor in the counter. So that means that instead of having to have a controller, a microcontroller, or a Pi or a CPU, you can set the scaling factor so that you can turn that counts per revolution into degrees. And so it literally means that all you need is the encoder and the counter. But this is an incremental encoder. So one of the things you got to have if you want to be foolproof from the standpoint of losing power is you have to have some way to back up the electricity if the electricity goes down. So that's what this little box is. If you see it right here, it's sitting right here. That's a little 12-volt battery backup unit. And that's what you see here. That will support the operation of this counter for up to 8 to 10 hours without power. So it turns that incremental counter into the equivalent of an absolute encoder and counter. And even if you lose power on the counter, you don't lose the scaling settings. So this thing turns out to be pretty bulletproof, and there's only 3 components. There's the battery backup, there's the counter, and there's the encoder. Now, one of the drawbacks, of course, is that this setup is local, but an awful lot of folks don't need to have remote position indication. Local's just fine. And so this kind of satisfies the requirement for that. But going into a little more detail on that, And he really cuts it off here. But anyway, here's the counter, there's the encoder. This is the entire schematic. There's 5 wires that connect the counter to the encoder. And the battery backup, of course, is 2 of those, which provides the 12-volt DC. But that's literally all you have to hook up to make this thing a high-resolution, repeatable, digital position encoder for either elevation or azimuth. And but the magic here, the magic in doing this is being able to configure that counter. And you would think, okay, there's a couple buttons on the back, no big deal. You're absolutely right. However, you've got to set the scaling factor, and you have to set the significant digits, whether it's azimuth or elevation, you change the number of significant digits. So on a 1,000 point per revolution or 1,000 pulse per revolution encoder, if you want to show 0 to 360 degrees, you would need you get a 0.36 degree per pulse resolution. Now that's a fairly low resolution. It probably would still work for my 3 meter, but I'd rather have it like 1/10 of a degree per pulse. But the other good thing is that it doesn't require any CPU or MCU, and you set these scaling factors, which are non-volatile, and you set the significant digits, and you do all of that, and you would think, yeah, okay, I'll just set those and everything will be great. Well, I got this counter from eBay.
Yeah.
And
no, that was my copy.
This is what came with it.
Yeah, no.
That's
brilliant. I didn't know if you wanted anything added to it.
Hey, guys, somebody's got their mic open.
Oh, no problem. No, you got it. Thank you.
So this is what I got with the eBay, off eBay for the counter. And I don't know Chinese. Some people might. I thought maybe I would take it down to the local Chinese consulate in Houston and see if they would decode it for me or translate it. But I asked the folks at the company that provided it if they would give me an English translation, and they were very quick and very efficient at telling me no. So, which, it's their decision. But so I figured out, well, I've got this thing sitting on my desk. I might as well try to figure out what it does. And so I spent time trying to understand what this is basically the configuring menu. And I basically spent time trying to figure out how to do that. And I did. So basically, this is just kind of a real quick example of how you do this, but there's 2 push buttons inside the back of the counter. And if you, for example, if you click the first button, then the second button, the display on the front of the counter will show 232. If you click S1 twice, then S2, then the display shows the scaling factor, and you can change the scaling factor to anything represented by 2 significant digits. Now, it would be nice if it could be 3, but it's really only 2. So it means you have to pick the combination of your gearing and the gearing and the encoder.
Hey, Bruce, I think you're unmuted again.
You're hearing you, Bruce.
Oh, okay. Yeah. You're hearing my wife bring me coffee. By the way, while I'm unmuted, one of the things I want to say is that I need to find out where the proceedings are. I just got to the conference, had a bunch of tie-ups this weekend. But anyway, where are the proceedings? And then I'll come down here and mute things.
Yeah, so we're putting together an electronic proceedings at the end that we're going to provide to everybody. So it's not ready yet.
Okay, thank you.
Okay, so anyway, we'll talk a little bit more about picking the right scaling factor to get you to a high resolution. But with this setup, you can get down to, given the reasonable encoder points or pulses per revolution and reasonable gearing, you can get down to 9/10 or 9/100 of a degree per pulse. So you can make this thing as probably a lot more accurate than you need it to be. And so anyway, this you do use these switches to change the scaling of the counter. For example, if you just had an encoder that had 1,000 points per revolution and you wanted to just hook it up as a direct, not geared kind of azimuth sensor, you'd get 0.36 degrees per pulse. If you geared it 8-to-1, then you'd have basically 2,400 into 360, which would give you 0.15. And that is in fact the case on my unit, where I have that 8-to-1 spur gear tied to the encoder, and that gives me 0.15 per degree. There are lots of different methods available for mounting these encoders. You can see here that in my particular case, I have a big spur gear that's on the azimuth, as I showed you a minute ago, and there's the small spur gear that is directly tied to the encoder. There's other ways of doing this. Of course, you can gear it like I did. You can use a gear belt or a cog belt that doesn't slip. You can use it direct. You can use it as a friction drive, two rubber kind of wheels on each other. You obviously want to make it so that there's minimal backlash and minimal slop in that ratio. But if you do, then you can gear these things up to really provide all kinds of accuracy.
Or update.
Hey everybody, I'm Way 31, morning meteorologist Grace Anello. We've had a lot going on this morning.
Dr. Wayne, please mute.
Saturday, things are looking okay right now. Quite cloudy. We still have some.
Hey guys, on Zoom, can I ask you something? Is there some reason why you hate me?
Nothing personal. We step on everybody's.
Yeah, okay. All right, so let's go on here. So that's how you would do something with azimuth. For altitude, there's a couple different things you can do. You can try to build your own inclinometer by having a pendulous weight to gearing to an encoder. I've tried that, and it's not a very successful operation because there's too much friction in that to really give you a good reading. You can, however, buy encoders that are inclinometers, where they have a very low friction transmission between the pendulous mass and the encoder. This one was a 1,000 point per revolution, so actually it's only 250 pulses for 90 degrees, but that would you could certainly use that. That's what we're talking about here. If you had 90 degrees and it was 1,000 and you're only using a quarter of it, you'd be back at 0.36 per degree. But again, these are all things that you only have to set just one time on the back of the counter and you're finished. So it's really turns out to be a really easy way to set up a position sensor. Now this is a demo unit that I just put together to come out here. If you look at this, I just have a protractor, 360 degree protractor on a steel plate here that is tied to the encoder through a 3-to-1 gear, spur gear thing on the back. And that is wired into, the encoder, or the encoder is wired into the counter. And you'll notice that if I turn this in either direction, it tracks the count pretty accurately and very accurately. And if you go up to, say 250 by the pointer here, it's reading 249.95 just because there's a dither there of the resolution of the counter. But for our purposes, with those three components, components of this little battery backup unit and the counter and the encoder, you've got yourself a position system, and how you put that into your mount or hook that up to your mount is totally up to you. You have a lot of flexibility in that area.
I'll show that again, because while you were talking, he wasn't quite on, so.
Oh,
Yeah,
To make-
I stopped the screen sharing.
Oh, okay.
To make sure.
Okay, can you see it okay? Okay, so if I were to go up to say 300 degrees here, not quite there, but 300 degrees here, I'm, well, in this case, it's showing 299.16, but that's because I don't have it pointed quite right. If I go down and go to 210 degrees, there's 210.72, because again, it's just not quite on the pointer.
So Bob, would that be, if you're gonna use it like this, obviously you need to turn, that's your encoder here, but the one you believe is the one on the digital showing here, and the other one's just a mechanism to sort of aim it.
Well, that's right. I mean, the encoder is tied to your physical antenna drive or azimuth axis. And there is simply a cable that goes from that encoder over to the counter.
But how would I, in practice, if I wanted to get it to 210 exactly, because it was what you just said, what's the protractor would really be hooked up to your azimuth, right?
Yeah.
Okay, so,
Well, no, the protractor, this is just a way of being able to give you a visual correlation between this and this.
no, I get it, but in
Yeah.
practice, what you'd have is, what the protractor is, would be hooked to the motor or whatever.
It will be hooked to the axis of your azimuth axis.
Right, so how does it know that I want it to be 210?
Well, the setting that position is dependent on either the motor that the calculation you've made that an azimuth of 210 and an altitude of 45.2 takes you to that object or not.
I'm way more simple than that.
Okay.
So I'm sitting here, I'm trying to control the antenna.
Yeah.
Here,
Yeah.
okay, so I want to move it, so it's at 210 right now, right?
Mhm.
So I wanted to move from 210 to 300.
Yeah.
Okay. Something has to tell it that I'm moving from 200 to, or 210 to 300. Is it hooked up to a computer
No.
interface, or how do I?
No, this is a local display, which means you would have to walk up to your antenna and turn the azimuth to get it. But if you turn the azimuth, it will give you the precise.
So it's reading it, it isn't controlling moving.
Oh, that's correct. Absolutely.
Okay,
There's
that's
no
the key.
control. There's no control mechanism here at all. It's simply if you change the altitude or you change the azimuth, this will show you exactly what you're changing it to.
And then if you wanted to go to more complex, you go to where you did with the Raspberry Pi and all that.
Right, and in that case, what's happening in the case of the Raspberry Pi is that it is, in my case, I was sending over a serial connection out of the Raspberry Pi. I was sending the azimuth and altitude into the house, into a control program that basically took that value coming from the antenna and compared it to a calculation that was being made in the program that converted the declination of the right ascension to altitude and azimuth. It was comparing those two and saying, okay, drive the motor up, drive the motor down until you get in that range. It was basically a gap controller, and that's what we would call it in control lingo. But it's a gap controller that will control that position within a very narrow tenth of a degree, quarter of a degree, whatever. Yeah, but there's no element of control here. This is simply a position system. But for the most part, you know, things like scope in the box and other things like that, if you hook this simple encoder to the altitude azimuth or azimuth axis, then you can get a very precise position for those two axes without any other kind of hocus pocus.
How much does all this cost?
This, let me show you. Go back to the, when you're ready. I forget the exact numbers, but this encoder on the back was about $20, $25. The counter was like $18. The battery backup was another 20 bucks. And so you get those three components and you got yourself a sub-degree display for position that is repeatable and accurate and basically functions just like an absolute encoder, because you don't lose the settings in the counter if power goes down, and you don't lose power because you got a battery backup that will support this thing for hours, literally. Here's the, how do I go back with the thing if I, on your particular setup here? Normally you get previous on PowerPoint.
No, backspace. That'll work.
Okay.
Backspace and enter.
There we go. All right. So if I go back here, this was, this particular encoder was $26 on eBay. The counter was 18, and the battery backup was 26, although I've seen it for 20. So anyway, but that's really all there is to it. And it's, the thing that impresses me about it is that having done this and knowing what that cost me and the time that it took me to buy it, can configure it, program it, build it, install it, and all that kind of good stuff. Yes, it provides remote information, but if I wouldn't, I wouldn't think anybody that had just a scope in the box with no motor controller would want to do that, But it's, this kind of thing is very doable, from a standpoint of a pro thing. On the reason why you might want to do it, it's really relatively inexpensive. It's simple to implement. There's only 5 wires that you got to hook up. Question?
I do.
Okay.
So given that the sensitivity, if I understand right, is 1/3 of a degree.
It's 1/3 of a degree only because there's a 3-to-1 gear up on this thing right here.
I get that. So the question then becomes, how do you calibrate it to the actual physical setting of the dish out there
Okay.
so that you can make sure that you're 210 degrees?
Yeah.
Versus whatever.
The way I'm doing it, and this is a little, this is also covered in those articles that were in the journal, but let me go back here. Oops. I think I blew it up. Here, what do you have to hit her to get a full screen on?
It's
Can I erase some of this?
Yeah.
Okay.
yeah.
There we go. Okay, here's, let me draw this, and I'm standing in front of somebody, I'll move. Happens to it's on. If you have the antenna and you have the mount, and I have, in my case, I have a garage that's right here, so I don't have any kind of low access to a horizon in the south. But if you look at the azimuth here, and then there's all this mess up here, which is the elevation. In my particular case, I put a little up here in the basically the frame that with the axis that tilts the antenna up and down, I put a laser pointer, a weatherized laser pointer up here tied to the elevation axis. Okay. I put a marker here that would say like 276 degrees, 31, and 63.11 degrees elevation. Okay. Because over a period of time, I decided where the sun was at a given time during the day. And from calculations, I knew that sun at that time of day was at 276 degrees, 31, and 63.11. And so I manually moved the antenna to point at that, looked at a total power display and made sure that it was maximizing. And then I said, okay, I'm pointed in the right space for these coordinates. And so what I did is then I lowered the antenna to where the laser beam was pointing right there. And that was it. Then I had a calibration mark. And then I basically set the, in my system, I have the ability to manually or to set it because it's remote. Here, what you would do is you'd unscrew the little small gear, and you would turn it manually until you got that reading. Then you put the gear back on it, lock it down, and then at that point it's calibrated. And you would do the same thing on the elevation axis. So then if you got all screwed up, like the other day, we had a windstorm that wrapped my antenna around the post and broke some cables and everything else. When I put it back together, I made sure that pointer moved the antenna both elevation-wise and azimuth-wise until that pointer was pointing right there. And then I knew that I would set my counters to those numbers and I'd be calibrated. And if you don't have a garage to put that on, then you can always, put a post in the ground or something with a target on it or something that doesn't move. And you would have a calibration point. That's how you would go about calibrating. And once you do that, of course, it's for all intents and purposes done. You don't have to do anything else except use it. And if you want to change that in the future, then you simply pick out another object that you know exactly where it is from calculations, and you make sure the total power is where you want it. And you then put another registration mark on some fixed pole or something, and that tells you where you are when you're pointed at that with a little laser pointer. And I literally took a laser pointer like this, and I put it in an aluminum box and sealed it and all that, and ran a switch to the battery so I could turn it on and off. And that's how it sets. And when I pointed at that object on the garage, I know that's where I'm pointing. So did that answer your question? Okay. So if we could go back to that last page, and then I'll be out of everybody's hair. The conclusion thing, the next slide now.
All right. Okay.
And if anybody wants, I've got actually out in the car, I brought an encoder, and I brought one of those counters. If anybody wants to take a close, hard look at it, I'll be more than glad to let you look at it. If you want to come up here and look at this, move it around, convince yourself it actually works, that's fine too. Anyway, it's a good local display for the antenna. It is not suitable for remote monitoring, remote display, because there's no easy way to get that data unless you want to try to hack the board and get the coordinates off the board. But there is no really easy way to get those coordinates off that board. But it is great for local. And of course, you don't need a computer. and or any kind of controller unit. The negatives here is that, just as I said, it's hard to share the position with any other program because you don't have a way to transfer data to the program. And you will lose the position if you don't use a battery backup unit. You don't have to use the battery backup unit. You can just connect it to 12 volts, and you won't lose the scaling of the counter. But if you lose power, you will lose the current position. So this is what keeps you from having to worry about that. And I pulled the power plug like right now on it at the house and kept it running for hours and hours and hours. And I finally got tired and went to bed and plugged it back in. It was still working just fine. And so you can, it has no effect on, it is still supplying 12 volts to the system. Okay. Any other questions about it? I hope if anybody's interested, I'll be more than glad to help anybody if they have any questions later on about doing it on theirs, on their mount.
Question?
Sure, question.
I was wondering if we go back and look at your articles in the SARA journal, are you presenting the exact same material, or is this new improved things that we need to know?
The information that's in the SARA journal is I think a fairly comprehensive view of the remote position and control system on a 3-meter antenna. It is not this thing that I'm talking about today. The thing I'm talking about today is a local display that can be put on a scope in the box or any of that kind of thing that you want to get an accurate position locally. The thing that's in the journal is not only a more complex remote and local position system, but a full control and tracking system for the antenna, including motor drives and everything.
Okay, thanks.
Sure.
And so I have a question too. Jack, do you
Okay.
have any kind of like micro switches or anything for end of travel to make sure if you do get out of whack that you shut things down before you hit the stops or tear up your cable?
Yep. If you look at the article, I think I put it in bold print. I said that anytime you try to build a drive system for an antenna, you better have limit switches installed. And I found that out the hard way. I've wound up my share of machine tools and other things without limit switches, so I wouldn't recommend any kind of an automatic drive system without limit switches. And it doesn't make any difference whether it's a milling machine or a telescope mount. You can do a lot of damage if you don't have those. Any other questions? Okay, thank you very much.
Thank you.